Let's see an example on a simple pendulum. So it is an example of a vertical circle, okay, assuming that the radius is just the length of a string, and this is a mass, and it also has a tension T, capital T, and it goes around in a to and fro motion. Okay, and we are asked to calculate the velocity at B as it passes here, and the tension in the string at B. So remember that the tension here is the centripetal force. Okay, so it is at position B, which means that in the vertical circle, in the vertical motion here, it would be here. So when angle is 0, when the theta angle is 0. So at this position, we have T and we have mg in the opposite direction. So let's find V at B. So the velocity at which it passed through B. So as it goes from A to B, it loses potential energy because it was initially at a height of 8 millimeters. And at B, it has lost this energy and it has been converted into kinetic energy at B. So we can say, using law of conservation of energy, so EP lost is equal to gain in kinetic energy. Therefore, it is mgh is equal to half mv square. So this V is at B. Okay, we can cancel the mass and we can just put V as a subject, 2gh, and just substitute the value. G is taken as 9.81 times the height, which is 8 millimeters. You have to convert it into meters. So 10 to the power minus 3 meters. So if you calculate this, you would have a value of approximately 0.396 meters per second to 3 SF. Okay, and now second part, we are asked to calculate tension in the string at B. So we have to use this diagram here. Okay, so at this point, the centripetal force is toward the center, and therefore the acceleration is also toward the center. So we can say that the net force is the mass times acceleration, which is a centripetal acceleration, and the net force is T minus mg, because as the acceleration is towards the center, therefore T minus mg, which gives you m. So centripetal acceleration is v squared divided by r. Okay, the tension would be mg plus mv squared over, so the r is the length of a string, so we can just put L over here. So just replacing the values, so it is 0.1. So the mass is common, I take it outside the bracket, so 9.81 plus v squared, which is 0.396 to the square, divided by the length of a string, which is 0.2 meters. And therefore, you will have a value of about 0.126 Newton. So this is the tension in the string. This is a very simple example of a vertical circle. Now let's see motion in a horizontal circle. So motion in a horizontal circle, which is also called the conical pendulum, because it looks like a cone. So in this, we have a pendulum which is fixed at a point, and it will go around a horizontal circle. So it is more like a cone shape. So the bob would travel along this horizontal circle. So this is a length of the string. Let's call it L, capital L. This is an angle theta. And there is a tension in the string T. So this is a radius of the circle. Let's call it R. So the motion would be in this direction. Okay, so the object is of mass m, okay, and it's traveling along this horizontal circle at a velocity which is at the velocity of v, which is constant all along the circle. So the total mass of this is m, and traveling along the circle of radius r, capital R. So let's assume that the period of revolution is given by, we call this symbol the tau. Okay, is given by tau. So now we have to find the tension in the rope and the angle theta. Okay, now we assume that Newton's second law is applied over here. So the net force is mass times acceleration, which is the centripetal acceleration. Now, what forces are acting in this diagram? So let's see the forces that is acting here. So if this is theta, we can say that this is also theta by geometry. And therefore, if this is theta, we know that this length is t cos of theta, and this, it is a force, not a length. So this force would be t sine of theta, and this force is directed towards the center of the circle. Okay, and this is providing the centripetal force. We can just write over here that the centripetal force, which is t sine theta, is towards the center, is m times the acceleration, which is the centripetal acceleration, which is v square divided by the radius, capital R. So this is just the first equation of motion. Now, we can also have an equation for the vertical force. So we already have a vertical force of t cos theta. We also have the weight, which is mg for the mass. We have the weight. So using this, we can say that the forces balances each other. The vertical forces t cos of theta is equal to the weight of the object. So we have a second equation, and therefore we can now calculate the angle theta. So we can divide the first equation by the second equation. So this will be t sine of theta divided by t cosine of theta, which is equal to mv squared divided by r divided by mg. And therefore, the tension cancels out each other. We are left with the tan of theta, which is equal to, so the mass will cancel out each other, and this will give you the velocity square divided by the radius times the gravitational acceleration. And now we can calculate theta, which is tan inverse of this. Okay, so theta we can calculate, and now let's see how we can calculate the tension. Okay, so to calculate the tension, we just need to replace the theta that you have calculated over here, just replace it in the first equation. So to calculate tension, replace the value of theta in equation 102, and you will get your answer in Newton. Okay. Now we can come up with another equation. So let's see that we have assumed that the period of revolution is given by tau. So for this, now we have the horizontal circle. Here is the length L, and this is R, the radius of the circle. Now in terms of length and the radius, okay, we can come up, if this is theta, so we can come up with another equation that the R, the radius, would be the length of the string times the sine of theta. Okay, so by simple geometry. And you can see here, this is also theta, so this would be L cos of theta, but this length does not exist, so we know that the R should be the L sine of theta by simple geometry. Okay, and now we can say that the velocity is given by R times omega, and omega is just 2 pi over the tau, the period of revolution. So we can just replace everything. The R is just a radius, so it is L sine of theta multiplied by 2 pi divided by the tau. So this is the velocity at which the particle is traveling. So we can just simplify the things. So 2 pi L sine of theta divided by the tau, which is a period of revolution. And you can also come up with this equation. So let's underline this one. Let's look at an application of circular motion. So suppose you are in a car and your car is traveling and goes on a bridge. So suppose a bridge can be thought to be a circle, and it would have a radius of r, and so you are traveling at a velocity v. So v is tangential to this circle, so to this bridge, and So your car would have a mass and a weight, which is mg, and also there is a normal force acting in opposite direction to the weight. So by Newton's second law, we can say that the net force is the mass times the acceleration. And the force that is providing here is a centripetal force, which is directed towards the center of the circle. And therefore, the net force would be mg minus the normal force, and this is equal to m times the centripetal acceleration, which is v squared divided by the r, the radius. And therefore, to calculate the normal force, we can say that it is just the mass multiplied by the g minus v squared upon r. Okay, this is an equation to calculate normal force. So at some point, if v increases, the velocity increases, at some point it would cause the body to leave contact with the ground and just fly off the bridge like this. So when the body leaves contact with the ground, meaning that the normal force is 0, because it is no more in contact with the ground, so there is no normal force, it is just 0. And therefore, what happened at a particular v, suppose at a particular velocity v, the normal force would decrease until it is 0. So the normal is equal to 0. And since there's no normal force, therefore we can replace in the equation by 0. So it is just m times g minus v squared over r is equal to 0. So g minus v squared over r is 0, which would give you, if you want to find the velocity over here, it is just v squared over r is g, and v squared is equal to g times r, and therefore the velocity is the square root of g multiplied by r. So this is the speed where the car is on the point of leaving the contact with the bridge, and it will fly over and goes in air. So it will leave contact with the ground. So at this speed, it is about to take off. But we can say that if v is greater than this speed, then the car will just leave contact with the ground. Okay, so what I'm trying to say is that here is a bridge, so the car would just flies off, leaving contact with the ground, and flies off. Now let's see an example where we can calculate this speed where it leaves the contact with the ground. So let's say, for example, we have the bridge. Okay, here's your car, here's the velocity v, here's the r, and this is mg. Let's suppose that the radius is 8 meters. So now we have to calculate the maximum speed v, okay, of the car, that the car can travel over this bridge of radius 8 meters without leaving the ground. So let's calculate this speed at which it is about to leave the ground. Okay, so we know that the net force is mass times acceleration, and therefore it is mg minus r, because the centripetal is towards the center, which is mv squared over r. So r is a normal force. Okay, so R is just m times g minus v squared over r. Now, if we put this to be 0, we'll have this equation. So if you solve the equation, you will have this v is equal to gr to the square root. And now you can just calculate this speed. So it is 9.8 multiplied by the radius of the bridge, which is 8 meters. And the speed is about 8.86 meters per second if you calculate it to 3 significant figures. Okay. Another example of circular motion, so an application of circular motion could be a car going around about. So this is a roundabout. So here's your car. You are turning in the direction of a circle, and your speed would be tangential. Let's call it v. So this is a center, okay, and there's a force that is providing the centripetal force, and it is the frictional force between the tires of your car and the road surface. So when the car is going around a corner or a roundabout, it is partly the frictional force between the tires of your car and the road surface that provides the centripetal force. So let's call the frictional force Ff. So small subscript f. Okay, and let's suppose that this is of radius r, and there is a frictional force of Ff. So you know that frictional force, so Ff, is given by the coefficient of friction multiplied by the normal of the body, the normal force. So if a body is in contact with the ground, okay, it always have a normal force, and the weight is acting opposite to the normal. So in this case, we say that the normal is equal to the mass times the gravitational acceleration. So we can just replace the normal with the mg, the weight of the car. Okay, so this is a friction, and frictional force is providing centripetal force. Therefore, centripetal force is just, we can just write it as mv squared over r. R is the radius of a circle here, and Ff is just mu times mg, which is mv squared over r, and the mass cancel out each other. So we can calculate the velocity to be mu gr, and the velocity is just the square root of mu gr. So in order to calculate velocity for a car going around about, so you have to know the coefficient of friction and also the radius of the roundabout, and then you can just replace it in your equation. So friction will depend on the day. So for a dry day, okay, the friction can be a large number, and for a rainy day, it can be very, very small. So it can be a fraction of the normal friction itself. So now let's see what is banking. This is another example, another application of the circular motion. So banking is when a car or any body, okay, a body is going at a plane which is inclined at an angle. So it is an inclined plane, and it is going around, okay, So here's let's suppose it is a car. This is the tires of your car. So it is going here, so towards you, it is going towards you, and therefore the center, so we know that this would be the mg. The normal is normal to the contact of the plane, inclined plane, so this would be the normal. And therefore, if this is the angle theta, by geometry, you can also prove that this angle here is theta. And therefore, if you resolve the forces around here, you will have n cos of theta, and you will have here the n sine of theta. And therefore, this is providing the centripetal acceleration, assuming that here is the center of a circle. Let's suppose this is the center of a circle. Let's call it O. So this is a O. Okay, so this is a O. So the radius is this, from the center O to the plane. So now you can see that the balance force is a mg and the n cos of theta. So we can just write this, n cosine of theta is the weight, and also by using, so this is the first equation, and by using Newton's second law, you can say that the net force is ma, and the centripetal force is in the direction of the n sine theta. So this would be n sine theta, which is a centripetal force because it is directed towards the center of the circle, and this is just the mass times the velocity squared divided by the r, the radius of a circle. So this is second equation. Now we can just divide the second equation by the first equation. Let's divide second equation by the first equation. You will have n sine of theta divided by n cosine of theta, and this is equal to mv squared over r divided by the mg. Okay, and here the normal cancel out each other. We have sine over cos, which is tan of theta. Tan of theta is, so the mass cancel out each other, is v squared divided by g r. So this is the, so now you can calculate the angle theta, so tan inverse of this v squared divided by g r. Also you can calculate v squared if you know the angle, so v squared is equal to gr tan of theta. So to calculate angle, you use this. To calculate the velocity, you use this one. Okay, of course, if you know the angle theta. And to calculate the normal force, you just replace the theta you have calculated in the first or the second equation as before. Okay.